So thanks a lot. Yeah, I'm a replacement for another candidate, so I should have been the chair, but thank you for giving me the opportunity to talk here. Else you would have seen me in a pre-recorded talk. So I'm going back to the Fornax cluster. We heard yesterday from Katja Farion about the F3D survey that is concentrated on the galaxies, and I will go a little bit in their outskirts, in the intercluster regions. And it's mainly work of my student Avinash Chaturvedi, who has also a poster here. So what is the advantage to go to very nearby galaxy clusters, right? You have the resolution, of course. You can look into dwarf galaxies resolved, getting the luminosity function. You can go to the diffuse low surface brightness galaxies. You can get in the outskirts of the galaxy halos in the intercluster light. You can in detail study the giant early type galaxy structure formation and maybe the dark matter content. You can also try to find then subgroups that are falling in and disangle maybe the assembly history. But here I want to concentrate on the compact objects, which are globular clusters, ultra-compact dwarfs, nuclear star clusters, as tracers of this galaxy assembly. So why the Fornax cluster? So you see a nice image. This was taken with the Las Campanas. A long time ago, we have a central giant elliptical that has an extended halo and has many globular clusters, 5,000 or so. And you can really get spectroscopy down nearly to the tip of the luminosity function, minus 7.5 in MV. So you can get thousands of velocities. A bit annoying are the foreground stars. You have contamination, of course. And you can resolve, as I said, nucleated dwarf galaxies and the ultra-compact dwarfs. The first imaging was done nearly now more than 20 years ago. This is a Fornax cluster catalog, and we still name these galaxies according to this catalog. So what I'm interested in is to use these global clusters as tracers of interactions and the assembly history. So this was a simulation by Becky also a long time ago, where you have in the middle gravitational potential of the central galaxy, and you throw another galaxy with a big global cluster system into that. And then the global clusters will be, of course, tidally released and tidally stripped, and you should see them in the phase space somewhere. And the ones that are first stripped are the outer ones, which are normally the blue metal poor ones. So this is a simplified model, what you would expect for such a kind of accretion event in the velocity. So in the phase space, a kind of cone shape, or in the, well, in the spatial distribution, of course, some kind of, you see the orbit, or in the angular distribution, you see some sine curve. Or you can also go to dwarf galaxies, and that might be also very interesting. So if you have a nucleated dwarf galaxies entering the galaxy cluster with the global clusters, so the tidal radius will shrink, of course, while it's falling in having the tidal tails, and the outer globular clusters are lost, while the inner globular clusters actually might still, because of dynamical friction, fill the nucleus or build a nuclear star cluster even. So the observation goals for spectroscopic surveys would be to find signs of accreted global clusters in the phase space distribution, maybe to find remnant nuclei, these UCDs. So indeed, so the first spectroscopic surveys started more than 20 years ago in the late, 20 years ago in the late 90s with KEC, with AAT, with NTT, and the 2DF project. And independently, many of us found then very big globular clusters that are called nowadays ultra-compact dwarf galaxies. And they fell in the size luminosity plane, some kind of an intermediate region between the globular clusters on the lower left side. This is a galactic globular cluster system. You have the elliptical sequence down to the compact ellipticals and the dwarf ellipticals here on the upper branch. And you see that these ultra-compact dwarfs fill this space in between. And there were some studies in the last 10 years, that the most massive UCDs indeed have supermassive black holes that can have up to 15% of their mass. So this was a proof that you can, with targeting this very massive star clusters or ultra-compact dwarfs, you can follow the galaxy evolution of nucleated dwarf galaxies that have been there in the cluster a time ago. There are many simulations out of this. So there was a milestone study for the spectroscopic survey of global clusters in the Fornax cluster, which is by Schubert et al. 10 years ago, more or less, where she targeted 700 globular clusters, mostly with FORCE2 and GMOS. And they were selected with Washington photometry, which has an advantage of a very blue filter, which is important for pre-selection of globular clusters. And you see that there is already a very nice spatial distribution. And the results were that in the phase space, you see a difference between the red globular clusters, which we call them red because they are probably more metal-rich ones, and they follow very much the component of the galaxies and are more compactly concentrated also in phase space. And then the blue globular clusters that show a very irregular behavior and higher velocity dispersion, as you can see on the right. So this is velocity dispersion against color. And so you can make genes models, you can get the masses of the central galaxy or out to the galaxy cluster. And then you can find that maybe the red ones are more isotropic, maybe slightly radial. The blue globular clusters are tangentially biased. And this gives you hints of the formation history of these galaxies. So along then, in the last 5 years, there came this nice Fornax Deep survey done with the VST Omega CAM by Enrica Giudice in 4 filters. So this is only part of the images. And with this survey, one could pre-select again globular clusters in these 4 colors and then look at their spatial distribution. And the finding was that the spatial distribution is elongated in east-west direction. So there seems to be in this cluster somehow an accretion along this line. And there are also, well, these yellow squares are all the galaxies, but there are also some features, some substructures that reach outside. Now, photometric selected globular clusters are not so, if you don't include the K-band, not so trustful, I would say. So there is some fluctuations, and you have to prove really whether they are whether the substructures really exist along these lines. So a side note, also in this deep images, you can find these ultra diffuse galaxies that were a hot topic in the last years because we have a very low surface brightness. Okay, and this low surface brightness, you can follow also the outskirts of these galaxies. And you know that in the center of galaxy cluster, there's this intracluster light and the outer halos reach far outside. So what you see on the right, lower right, this is a galaxy subtracted, and you see intracluster light between them in this east-west direction I mentioned already. And in the upper plot, you see as a blue contour, these contours of global cluster number densities. And you see that they somehow correlate. So it's entirely possible that you can use intracluster globular clusters as tracers of the accreted light and thus of the assembly of the central galaxies. Okay, so that's why we set up a while ago, 5-6 years ago, a VIMOS spectroscopic follow-up survey on Fornax. This was on enough GTO time. And to cover all this central region where you see these galaxy interactions, where you see these substructures. And since this is a conference in honor of VIMOS a little bit, and was meant to be also VIMOS conference, so there are I put some slides now how it was with VIMOS to observe VIMOS. So we had in total, you see here, 4,500 slits. So we pre-selected, so we wanted to have a very dense and homogeneous coverage of the central region. So you have to overlap. These are the 25 VIMOS pointings. And on the right, you see really the spatial distribution we got of all what was observed. So, and then who knows VIMOS observation, this preparation is quite tedious with VMMPS. So you have to have a pre-imaging, you have these 4 quadrants, and you have to make your slits. And if you want to be efficient, you make it manually mostly. Okay, and then you get this nice spectra of VIMOS, and okay, and then finally you have your spectra and can work on them. So this was done by my student Avinash, who did this with PPXF and the EMILES spectral library to go through all the spectra, excluding first emission line background galaxies, excluding also zero velocity stars. And so we found at the end 777 unique Fornax globular clusters, velocities. and they are distributed in a signal to noise and in the colors like you see on the right side. So this is a spatial distribution color coded by velocity. You might not see adding also all literature values, I should say, and the F3D work from Katja. So we added up to more than 2,300 global clusters. Here you see the velocities, but I smooth them a little bit, and then you might see that we see some kind of substructures. You have a high velocity orientation to the northwest and in the southeast. You have this east-west elongation. You have low velocities mostly on the east side here. Okay, and if you ask again against the color, now they are color coded, and on top of the photometrically selected global clusters, which is this white-gray distribution, you see by eye already that the red ones are more concentrated, and that mostly the blue ones are following these substructures, right? And then we made an analysis of how they really spatially correlate the confirmed intercluster globular clusters, so the ones with radial velocities, and what is their velocity distributions in these different regions of substructures. And it showed that this is really significant substructuring. On the other side, there is another deep survey, imaging survey, that looked at the spatial distribution of dwarf galaxies, and dwarf galaxies seem to be also not evenly distributed. They come in groups, they come in overdensities, and these overdensities more or less also coincide with this global cluster overdensities. So what we now have in hand, we have the velocity information, we have the photometric information, we have the color information, so we can make phase-space plots of red and blue global clusters. And there you see clearly that we now have went out to 300 kiloparsec, nearly half the real radius of the Fornax cluster. You can see in the red distribution the individual galaxies and how the global clusters cluster around, but maybe also overshoot in some directions. There might be some tidal interactions here. You see that in general, there are more blue globular clusters than red globular clusters. This is typical for intracluster stellar populations and the outer halos. So we can build up now a velocity dispersion diagram, so a velocity dispersion profile. So that's a bit busy, this plot. So it starts in the left with the radius. This is the inner 80 kiloparsecs. This was this work from 10 years ago. And you see here in this red, the red symbols are the red globular clusters. This was the old and the new work. They more or less coincide. The gray are all our globular clusters. So this was the situation. So there was a rising velocity dispersion profile in the very inner part. So an effective radius is by the chance only here 14 kiloparsecs. So we go out already here some 8 or whatever 5 effective radii. So this was this first work. Then there was planetary nebula added. This is this green curve to go out to 160, 70 kiloparsecs by Chiara Spiniello. And we see we can follow out, but we get even out to about half the virial radius and can follow the dispersion profile. You see that the red ones are following more or less the galaxy. So wherever there's a galaxy, of course, this can either bring the velocity dispersion down if only this galaxy is at this radial bin or dominating the radial bin, or bring it a little bit up. So what we tried to select only intracluster globular clusters. This is this pink curve, where the inner part you don't have to believe because we're cutting out 1399 basically. But you see that it is more or less a constant velocity dispersion of 300 kilometers per second. So what next? So this at the moment, as far as we are now in the phase of going back to dynamical modeling. First, genes analysis of this intracluster global cluster, so to constrain the dark matter of basically the halo of the inner cluster, not only the individual galaxies, but the whole halo. So, and then we try with this discrete tracer analysis and Schwarzschild methods to find also the substructures. So to find really the assembly history through orbital modeling of the globular clusters that are in the substructures that belong to galaxies or to the accretion, tidal accretion events. and add also to this information the colors and element abundances, and finally comparison with simulations. I know that the eMosaic simulations include globular clusters or star clusters in general, and the next ones, the next generation of these models go also to Virgo Fornax cluster like galaxies. So to add, of course, you cannot, we have the colors, and so to add also the element abundances, we did some 60 global clusters with very high signal to noise with force, and we preliminarily analyzed those, and you can get even an H distribution, a metallicity, and an alpha over ion abundance distribution, which might be then very interesting to connect to the whole assembly history. So I summarize here. So maybe you can read, but I want to make the last point. That is a very important one. VIMOS was a great instrument. Thanks a lot.